Good morning, everyone. Thank you so much to get the chance to present our Horizon project moderator. My name is Yannick Krabben. I'm from the Competence Center for Thermal Energy Storage in Switzerland, so in Lucerne, at the Lucerne University of Applied Sciences and Arts. To give a quick overview to the moderator project, so the way we work with data centers is really we focus all on the waste heat recovery system. We work with an immersion cooling system, where the goal is really to achieve a system with the highest possible temperature without having kind of a certain amount of thermal degradation of the server racks. Then we kind of use the waste heat, this intermittent availability, store it in a newly developed phase change material that I will go deeper into after. And then the third and the last part is actually also setting up the insulation material for this storage system. Then what we also look into is different case studies that we have within the project. So we look at different locations. We determine our 3 locations with different server units or different data centers. And there we really look into how we can use this waste heat that is stored in these phase change materials for other uses. So in industrial applications, greenhouses, and so on. Quickly looking into the consortium, we are distributed all around Europe. The pilot, or one of the pilots that is planned, is in Greece. So our data center provider that also developed now their own immersion cooling system is Synapsicon. They're located in Athens. So this is also where our first pilot will be built. Then I said HSLU and COBA, we work together at development of the phase change material and also the storage system actually. So how to get the heat in and out of the materials. Then we have Sintef in Norway that is doing some simulation works on the temperature distribution also in the immersion cooling unit. So how does the temperature affect the server? How can we achieve as high as possible temperatures of the dielectric fluid in the servers? Exactly. And what I will go into now real quick is something that we are mainly working on, so really into the material studies that we have done. And we're also, it is a 4-year project. We're also now halfway into the project, actually, with the first report that we had to deliver at the end of last year, which was on the material development and the testing of these new phase change materials that should be applicable within this temperature range of, let's say, 40 to 60 degrees, that kind of are allowed to operate an immersion cooling unit in. Then I will also look a little bit into the next task that we have to submit at the end of this year, actually, which is then really the system design. So how do we design the immersion cooling unit connected to the PCM storage and how it is operated? So we have actually developed 3 materials within the project, within this target temperature range. We work with salt hydrates mainly because they're cheap. They're non-toxic, so they're available. Basically, they're food grade, so they're also used in many food industries. We have now I said 3 materials. In the end, we focused mainly on this PCM 58 at the phase change temperature of 58 degrees C, and that is PCM 45, where we have now over 1,000 cycles tested of the materials within the testing unit I will show after. Real quick. In the end, we selected the PCM 45 for our first prototype because the temperature, the phase change temperature, is just low enough to be charged with a server unit, because there always, of course, we have this trade-off. If we increase the temperature in the immersion cooling unit, the servers will run less efficient. But of course, we cannot charge our phase change material. So one of the first tests you've actually done is in this 3-layer calorimeter. You see there the enthalpy distributed over the temperature, and you can see this nice enthalpy peak at around 49 degrees. So exactly what we are looking for in the phase change material. Then the second step, how we test this material. This is a setup which is so-called mini cell setup that was also developed within this project. The goal really here is to test PCMs at larger volumes, because everyone that has worked with scale-up production of phase change material knows this. You can test the material in small batches, but as soon as you go into several liters, it behaves totally different. So this has a volume of around 0.6 liters, and what you can see there is really tests all the way on the left is fully crystallized, then semi-charged, so semi-liquid, say 90% charged, and then 50% discharged again, so the crystallization process. And here it's also really important to observe visually how the material behaves. So do we have segregation? So do the additives settle down in the materials and all of these processes? Then some quick results on the performance of this mini cell. The way this is operated, we actually have a water circuit that runs through this aluminum body and then heats up the material inside the aluminum body, and also we can use the cold water to discharge it again. There's no direct contact between the water and the PCM, so it's all within this aluminum body. And on the left, you can see the inlet temperature of the water, and on the right, the discharge temperature then, with this nice plateau that we are looking for, exactly for these PCMs. And the most important thing here is actually the theoretical stored energy over a large number of cycles. That here are shown around 130 cycles of these 1,000 that we have done within the mini cell. And you can see there really that the energy stays quite constant, so the energy that we were able to discharge stays quite, doesn't degrade. Yeah. Then the next step, what we're going to do with this material, so together with Cova Thermal Solutions, we actually developed a larger storage unit, which is this so-called compact cell here. It's a 120-liter unit, and within this targeted temperature range, we are able to store around 12 kilowatt hours of thermal energy. One of the main goals also of this moderator project was to have a scalable product. So you can connect as many units of that system as you want. You can integrate different PCMs. Basically, it's a rather simple unit. In there, it's in the PCM, it's an embedded heat exchanger, FINT heat exchanger, with two circuits, so a charging and discharging circuit, to then efficiently charge and discharge the material. We have now also built the first pilot. The one picture you see there is actually a pilot that is in a multi-family building that was now operated for one heating season already. So it started to operate already last winter, just really this long-term testing. Then to sum up real quick, so we have achieved now two materials within this temperature range with a stability over 1,000 cycles. But of course, this has to be tested also close to the application, because now all of the cycles were pretty similar. So we have different, similar temperature distributions, similar kind of boundary conditions. The mini cell that was developed proved as well its test setup before then the real scale up to larger material volumes. Then it's really important to point out the importance of this PCM testing as close as possible to the application, so larger volumes and different charging temperatures like semi-charged systems and all of that. We used actually eutectics to depress the melting point of the phase change material. I will not go deeper into the material composition because Cova has still a patent pending there. Yeah, and it's just like really important to optimize the melting point for this immersion cooling system to get as close as the operation temperature, but still not have thermal degradation of the server units. And last thing, actually, I would like to use this chance as well to point out that we have our symposium coming up that I would like to invite you all of. Focusing on thermal energy storage. We're growing every year. We have now around 500 participants from industry and also from research. Yeah, it's in beautiful Lucerne, so come by. It would be nice to see some of you there. Yes, thank you so much.